In this video, I'm going to demonstrate one of the derivations of Euler's identity. So if you're not familiar with Euler's identity, this is what it looks like. It's an equation that says that e to the power of I pi plus 1 equals 0. And it's strange for a number of reasons. It's mysterious actually for a number of reasons. So for one thing, we've got these numbers that we're familiar with, 1 and 0, from which we can make all the familiar counting numbers, the real numbers. And then we've also got this imaginary unit I, which is defined as the square root of -1, from which we build the complex numbers. So even the fact that they're in the same equation is quite strange. To make things weirder, then we've got this quantity e, which is the exponential number, to do kind of with natural systems and exponential growth and other things. It appears in a bunch of areas of mathematics. And then the number pi we're familiar with, but we tend to associate that with geometry. So the fact that all these quantities are in the same equation is kind of intriguing and kind of strange. So I would encourage you, if you're interested, to read more about Euler's identity online. What we're going to do is try and prove where this identity comes from, or use one of the proofs. There's different ways to arrive at Euler's identity, and we're going to focus our proof on these guys here, which are called Maclaurin series. So Maclaurin series are an example of what's called a power series, and if you're not familiar with power series or Maclaurin series, then I would encourage you to watch this whole video, in which case you can pick up these ideas. If you are familiar with Maclaurin series and you've already seen these results and you know how to derive them, then you can skip over that part to the end of the video. And in the end of the video, essentially, we're going to piece these guys together and do a little bit of algebra that allows us to then make Euler's famous identity. So the first thing we're going to do is to start to explore Maclaurin series, and we're just going to derive each of these results one at a time. And I'm going to start with the sine function. So let's make a start with Maclaurin series for the sine function. So we're going to derive the Maclaurin series for the function sine x, but before we do so, let's just have a quick look at what Maclaurin series are in general. So a Maclaurin series is a specific example of a more general type of series called a Taylor series, and the thing that makes a Maclaurin series is the zero that I'll chat about in a moment. Basically, it means that the series is centered at 0. We don't need to concern ourselves too much with that, but just know that it's an example of something called a Taylor series. And a Taylor series and a Maclaurin series are both examples of what's called a power series. And essentially a power series is a way to represent a function using these different powers on the x term. So we're using this infinite series of x terms with these ascending powers, and that is what defines a power series. And in this particular Maclaurin series version of a power series, we're deriving the coefficient, the number in front of the x term, by using derivatives, and that's what makes these really clever actually, and also these factorials, but we'll chat about that in a second. So basically, to derive a Maclaurin series, we take successive higher order derivatives of the function sine x in this case, and that then allows us to start building up the series. And the series goes on forever, but it's going to be sufficient for us to generate the first 5 or 6 terms. And then we'll move on to the cosine function Maclaurin series and the exponential function. And we need all of those to generate our derivation of Euler's identity. So let's have a look then at the sort of formula, if you like, for Maclaurin series. We're going to use this for all 3 of our derivations. It basically says that your function f of x is equal to f of 0. Technically, it's actually f of 0 x to the power of 0 over 0 factorial. 0 factorial is 1, x to the power of 0 is 1, so effectively they drop out. But I'm putting this in to show the pattern. So it should be that this power here goes with the factorial. For example, the power 2 goes with the 2 factorial, the power 3 goes with the 3 factorial, and also that level of derivative. So this one technically, again, is actually an x to the 1 and a 1 factorial, but 1 factorial is just 1. So you can see the pattern here. First derivative goes with a 1 and a 1. Second derivative goes with the x2, the x squared, and the 2 factorial, etc. And that would carry on indefinitely. And that is basically the formula, if you like, for a Maclaurin series. So we're going to be plugging into that formula. To do so, we need to generate these successive derivatives and evaluate them at 0. So it's good practice to do this very logically. So we're going to start essentially by almost making a table, and we're just going to start with our f of x. So our f of x, remember, is the function sine x. And we don't need to differentiate it for this first term because we're just going to plug in 0. So f of 0, so that's going to be the sine of 0. So you're going to have to think a little bit about sine and cosine graphs, or whatever function you're working with. The sine of 0 is 0, so you could think about that off of the sine graph, or you might just be familiar with that value, so that's from trigonometry. So that's our first value. That's going to be going in here when we get to create the series shortly. Then we're just going to take successive derivatives. I'm going to go through this fairly quickly because we've got quite a lot of them to do. So the derivative of sine, I'm going to assume you're familiar with these. If you're not, then just look them up. The derivative of sine is positive cosine. So this goes to cos x, and then we're just going to evaluate that to get f prime of 0. So that's to generate this term. It's all these coefficient terms that we're trying to generate. So the first derivative evaluated is 0. That's a cosine of 0, which is 1. Okay, so again, thinking about maybe the cosine graph or whatever method you need to use to get the 1. So that would be like that. Then we're going to take the second derivative, so f prime prime of x. So we're differentiating cosine x, which goes to negative sine x. You've got to be really careful with the plus and the minus in these. It is easy to make a mistake. And then we're going to take that second derivative and evaluate it as 0. So it's a sine of 0 and then a negative in front. The sine of 0 is 0 though, so negative 0 is still 0. So it comes out to be a 0. And you'll see that there's going to be a pattern in these, and that's one of the cool things that makes this whole sort of Euler's identity work. The cyclical nature of these, I guess. Now we're going to take the third derivative. So we're differentiating negative sine x. The derivative of sine x is positive cos, so the derivative of negative sine x will be negative cos. So it's negative cos x. And again, we're just going to then plug into that. So the third derivative evaluated at 0. It's a little bit repetitive, this. And like to say, if you're familiar with these, you can skip over these already, but it's just to show where the result comes from. So we're putting a 0 in here. The cosine of 0 is 1. That's going to be minus 1 for this particular result. We're just going to do a few more. So let's go to the fourth derivative. So we're going to start to use, again, like Roman numerals is what the convention tends to be for this. If you differentiate cosine, you get negative sine. So it's going to be negative sine, which will be back to a positive sine. So we get sine x. And then again, we're evaluating that. Just doing the same thing every time. We're evaluating that at 0. And in a Taylor series, we don't evaluate at 0. It's only in this Maclaurin series. The sine of 0 is 0. And effectively, we're now back to the start, aren't we? We've gone in this cycle. We started at sine x, we've done these successive derivatives, and we've ended up back at sine x. That is a feature of the sine and the cosine functions. We'll see the same thing when we get to cosine. I think we'll do a couple more. So let's go the fifth derivative, which is the derivative of sine, which goes back to cosine like this. And then evaluating at 0, we're back to this point now. So it's going to be the fifth derivative evaluated at 0, which is this result, cosine of 0, which is 1. And that's probably, I think, going to be enough. Or shall we do one more? That's probably going to be enough. If we need another one, we'll do it in a moment. So what we're going to do now then, we're just going to plug these results in here. Remember, these are this is what we're after, really, these numbers here. And that's to get the coefficient numbers. So taking all of this stuff here, we can then write our Maclaurin series for f of x, which in our case is the function sine x. So this tells us that the function sine x, written as a Maclaurin series, can be expressed as f of 0. So f of 0 was 0. So you can put that in if you want, just to get started. We will drop it later. So that would be a 0 for the first term. It would be 0 times x to the 0 over 1 factorial, but that's all just going to become 0. So we'll just leave it as 0. Then we're taking f prime, the first derivative at 0, so this guy here, which is 1. So it's going to be 1 times x to the 1 over 1 factorial. So that's just going to be plus 1 times x to the 1, which is just x. 1 factorial is just 1, so it's x over 1, which is just x. The third term, f prime prime 0, is this guy here. Again, you can see that's just going to be a 0. So that would be like 0x squared, but that just makes it a 0. The fourth term, which is the third derivative evaluated at 0, this becomes a negative because it's a negative 1, so it's minus x cubed over 3 factorial. 3 factorial is 6, but we'll just leave it as 3 factorial. So that takes us to this point here. Next term's again going to be a 0. So you can see there's a pattern here, obviously. The zeros keep reoccurring at the same place. So we can skip over to the next term. So this, remember, went with the x to the power of 4. We would now be on the x to the power of 5 term. This one's going back positive, so it would be a plus. And it's just a 1 again for the coefficient, so it's going to be a plus x to the power of 5 over 5 factorial. So you can see if you tidy this up by taking out the zeros, this term, this term, and this term are disappearing, so you're going to get an x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. And that pattern that you can see will continue. So a couple of things. So we're only picking up, remember this is like an x to the 1, and effectively that's over 1 factorial. So we're only picking up the odd powers. The even powers are the ones that's disappearing for the sine function. And we're also alternating. So a positive term, negative, positive. The next one would clearly then be negative. It would also clearly be x to the 7 over 7 factorial. Then it would go back positive, and it would be x to the 9 over 9 factorial. And then it would just carry on that way. So that is the derivation for the Maclaurin series for sine x. We need the same thing for cosine x, and we need the same thing again for the exponential function. So let's just crack on with those next. So we need to make the Maclaurin series for cos x, just in the same way we made the Maclaurin series for the sine function. So again, we're just plugging into the same formula, if you like. The setup never changes. So we're starting this time with f of x equals cos x, and this should go very similarly to the cosine function, because when you differentiate sine and cosine, you just get the other function, either plus or minus. So we don't need to differentiate the first one, we're just making our f of 0 just to get the first coefficient. Just again, be careful that you pick up the correct values. Think carefully about the sine and cosine 0 values. So the cosine of 0, again, maybe thinking about the cosine graph, the cosine of 0, or to get our f of 0 is 1. Then we can start differentiating. So f prime of x, the first derivative of cosine, is negative sine. Got to be careful with the plus and the minus, that's the main place where you could trip up. So that tells us that f prime evaluated at 0 is going to be minus the sine of 0. The sine of 0 is 0, so that's just minus 0, otherwise known as 0. So second derivative, f prime prime of x. Differentiating sine x gives you cos x, so negative cos x then would be our derivative for negative sine x. And again, just evaluating this, so f prime prime at 0. Cosine of 0 is 1, like we saw up here, so minus the cosine of 0 is going to be minus 1, like this. Okay, we'll just carry on, do a few more. So the third derivative, differentiating cosine gives you negative sine, so this would be negative negative sine, so that's a double negative, so that would end up being positive sine. And again, just evaluating that third derivative at 0, the sine of 0, we've already seen this, is 0. So you can see we're starting to build up a pattern a little bit like we did in the previous derivation for the sine function. They should be very similar. And now we're starting in with the Roman numerals, so the fourth derivative of x, so differentiating sine just gives us cosine, and we can see now that after these differentiations we're back to the start, and that cyclical pattern would just continue from there. So the fourth derivative evaluated at 0, so the cosine of 0 again is 1. And again, we could do some more, maybe just do, shall we do one more? So we'll make it the fifth derivative evaluated at 0. So cosine differentiates again to negative sine, so we are literally just back to this point. And yeah, evaluating that at 0, fifth derivative evaluated at 0 is going to be the same result as we had here. Sine of 0 is 0, so negative 0 is 0. And then again, you would just carry on to generate more coefficients for more terms of your power series. So pulling these together to generate our Maclaurin series for cosine x. So we get cos x is equal to, so the first one, f of 0 is 1 this time. It's x to the 0 though, which basically is going to disappear. So the first term is just 1 because x to the 0 is just 1. So it'll be 1 times 1 over 1, which is just 1. Second one becomes a 0. So for this term, it becomes a 0. So it'll be 0 times x. But again, that 0 knocks everything out. So we'll just write in the 0 for the time being. Got to keep track where you are. So we're now on to this one, which is this guy here. It's a negative this time. So it's going to be negative 1x squared over 2 factorial. 2 factorial is 2, but we'll just leave it as 2 factorial. The third derivative again is a 0, so picking up that 0 every second term. So we're now here, but that's just going to be a big 0. Then we get back to a positive term, so we've got the alternating signs again, plus to minus. This one's a 1, we're now on to the fourth derivative, which I don't have up here, but that would just be a positive 1 times, this is our x cubed term, then it would be the x to the fourth term, which goes with the fourth derivative, and that's going to be over 4 factorial. And then the next one's a 5. The next one's a 0 for the fifth derivative, so that gives us a 0, and then that would just carry on from there. Next one would be a negative, etc. So we don't need to go really much further. We can see the pattern already, so we'll just tidy this up by pulling out the zeros. They obviously don't need to be there. So our first term this time is a 1, so this is for cos x. Then we've got minus x squared over 2 factorial, then the 0 again, then x to the 4 over 4 factorial, then the 0. So a negative term, a positive term, then negative, then positive. Next one would be negative. You can see it's going to be x to the 6 over 6 factorial. And this is all really because of the cyclical nature of the derivatives. That's why we're picking up these patterns. So that's then going to become a positive x to the 8. And these patterns, this pattern we can see with the even numbers here and the odd numbers for sine, the sine function, that's really going to be the key to unlocking later on the Euler's identity derivation over 8 factorial, and then that would just carry on. So that's basically all we need. We've now proven or found the Maclaurin series for sine x, and now we've just done cos x, so that's the first two. We need to crack on and do the third one we need, which is for the exponential function e to the x. So let's just get straight on with that one. So the third and final Maclaurin series we require for our proof of Euler's identity is the Maclaurin series for the exponential function e to the x. So it's a little cumbersome to generate these Maclaurin series. You can of course just look them up. I mean, these are well-known results. I just wanted to show in this video where they come from. So if you're familiar with these, you can skip over. But this one fortunately is quite straightforward, as you'll see in a moment. So f of x, our starting function, is e to the x this time. And we're just going to start by plugging in a 0 to get f of 0, just for our first coefficient. Anything to the power of 0, so e to the power of 0 is 1, so that just becomes a 1. So this one's really easy because you may remember that when you differentiate the e to the x function, the exponential function, it is just e to the x. And that's because of the chain rule. Like if this had been like a 2 in here, then it would be 2e to the 2x for the derivative. But because this is a 1 in here, essentially the derivative of 1x is 1, so we're picking up a 1 coefficient every time we differentiate. So we're going to get 1e to the 1x, or otherwise known as just e to the x. So in other words, e is its own derivative, so e to the x differentiates to e to the x. That then means, of course, that when we plug in here and do f prime of 0, we're just plugging in for the same calculation, so it's going to be a 1 again. And that would just keep going because they're never changing. So f prime prime of x would also be e to the x. And therefore, f prime prime evaluated at 0 is also going to be 1. So this pattern is just basically going to continue. So we don't really need to generate any more terms. It basically means that all of these coefficient numbers in the Maclaurin series for e to the x are going to be 1. So it makes it nice and easy to pull this one together. So a little bit less work to do this time. So the e to the x function is just going to be 1x to the 0 over 0 factorial. So that's just 1 times 1 over 1, which is 1. And then we've got 1x over 1 factorial. 1 factorial is 1. So we get 1x, or just x over 1. So just an x. So it's 1 plus x. This will be 1x squared over 2 factorial. So just x squared over 2 factorial. Next one would be 1x cubed over 3 factorial, so it's just x cubed over 3 factorial, and this just carries on in this really neat way. So the exponential function's got a very neat and tidy Maclaurin series. So you can see, maybe, hopefully, if you've already watched the part of this video where we did the Maclaurin series for sine and cosine, you will remember that those functions picked up either odd or even powers. And you can see that this expansion for the exponential functions got both odd and even. So it's the fact that this one has got both and the others have got odd or even that's going to help us pull this all together in the next part of this derivation. So what we've done so far is to pick up the 3 Maclaurin series, to derive those for sine, cosine, and e. What we want to do now is think about how we can pull those together to make the Euler's identity. So remember, where we're trying to get to is e to the I pi plus 1 equals 0. So we're going to make a start on that next. So now we're ready to pull together our Maclaurin series for sine, cos and e to finally arrive at Euler's identity. So we're going to start here with the Maclaurin series that we generated for e to the x, and we're going to replace the x with ix. Now that's going to seem a little bit weird at first, but that's just going to allow us to arrive finally at Euler's identity. So that just means that every term in the series with an x, we're going to change that term to ix. And we'll see later on why that is helpful. So the 1 stays as a 1, the x becomes an ix like this. Just be careful when you're applying the powers, because x squared, for example, becomes ix squared. So remember, you'll need a little bracket for that. So ix all squared over 2 factorial, and then just carrying on in this way. So ix cubed over 3 factorial, and we'll do a few of these just to make it clear what's going on. So ix to the power of 4 over 4 factorial. And what we want to do next is, well, a couple of things. First of all, I think we should get rid of those little brackets. I'm just going to do one more, so ix to the power of 6 over 6 factorial. And then we want to just think about, well, how we can simplify that. So let's just take a line of working just to get rid of those brackets. So we're going to make this e to the ix equal to 1 plus ix. Remember, when you're applying the power to a bracket that's got like multiple terms, you're applying it to each term. So this will become I squared x squared. So that first one then, that first term with the bracket becomes I squared x squared over 2 factorial. And we're just going to have to do this for all the terms. So I cubed x cubed over 3 factorial plus I to the 4, x to the 4. So a little bit monotonous at this point, but we need this. We've got to be careful, don't want to make mistakes here. Over 5 factorial, and then we'll just again do one more, so it'll be I to the 6, x to the 6 over 6 factorial. So if we think a little bit about these i's with the powers on them, let's do a bit of side working to think about that. So if you're familiar with I already and complex numbers, you might already be familiar with this pattern, but basically I is defined as the square root of -1, so it's called the imaginary unit. That means that if you take I and square it, so this would be like I to the power of 1, so if you take I and square it, that means squaring the other side of that equation, so squaring this side, squaring this side. If you square a square root, you just cancel the square root. So basically I squared becomes -1. Then we want to make I cubed, and we basically want to make all these I powers for these terms here so we can substitute in. I cubed is going to be I squared times I, but that's going to be -1 times I, so that becomes -I. So to generate an additional power, a subsequent power of I, you just keep multiplying by I. So multiplying here to get I to the power of 4, multiplying here to get -I squared. I squared, though, we know is -1, right? I squared is -1, so this is -1, which is otherwise known as +1, like this. Then if we wanted to get I to the 5, I'll just do that up here. I to the 5, well, that's going to be these, both multiplied by I to get I to the 5, which will be 1 times I, which is back to just I. So it goes in this cyclical pattern again. So then I to the 6, again, you'd be multiplying both sides by I. That would give you on the right-hand side an I squared, but I squared is just -1, and it's just going to carry on in this manner. So this would just be ... blah, 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 carries on forever. But crucial, this is crucial for our result. So we can pull those in over here. So the 1 is fine, that'll stay. The I here is fine, so that's going to be ix. And notice basically that some of these have got i's in them, and some of them don't have i's in them. Like there's no I here, there's no I here, but there is an I here, and there is an I here, and that's going to be really important as well. So the I squared, that's -1. So that -1 would come in front to be a minus, basically, x squared over 2 factorial. The I cubed is -I, so that becomes, let me actually just take that out. Rather than making it sort of a plus minus, we'll just make it a minus. So that I cubed becomes -I, so that's going to be I times x cubed over 3 factorial. I to the power of 4 is just a 1, so that becomes plus x to the power of 4 over 4 factorial. I to the power of 5 is I, so it's a positive I, so it's plus I x to the 5 over 5 factorial. So you might see where this pattern's starting to go. I to the power of 6. We might actually have to do a few more of these. So I to the power of 6 is minus 1, so that becomes a minus 1. So again, I'll just pull that minus here. So it becomes minus x to the 6 over 6 factorial. Yeah, I think we shall do a couple more. So let's go I to the power of 7. So that's just going to be multiplying both of these by I. So that's going to give us a minus I. And then I to the 8 would be minus I times I, which is minus I squared, the same as this here, which would be back to 1. So generating that next term is going to have a coefficient. So it's this term here, would be an I to the 7, which is minus I. So it's going to be minus I x to the 7 over 7 factorial. And the final one with the 8 is a plus 1. So it's plus just a number 1, not a 1i, just a number 1, x to the 8 over 8 factorial. And then that pattern would continue. Okay, so notice here we've got positive, positive, negative, negative, positive, positive, negative, negative, positive, blah, blah, blah. So we've got this pattern kind of going on in this expansion again, even after we've put in the ix. So there's a lot of symmetry, a lot of patterns going on in this derivation. Okay, so notice that some of these terms have got i's in them and some of them don't have i's in them. What we want to do next is pull those terms apart. So we're going to pull the terms that don't have an I and the terms that do have an I apart. So let's start with the ones that don't have an I. I'm just going to sort of put these in a bracket, I guess, to separate them. So we've got this guy here and this guy here. Okay, and then we've got this guy here, so plus x to the 4 over 4 factorial. The next one would be this one, which is negative x to the 6 over 6 factorial, and then this one will be the final one, but these would carry on forever. But the final one in terms of how far we're going, so that's over 8 factorial, and then blah, 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 that would carry on. So the next set are the ones with the I, so we've got an ix, like this, and then we've got, in fact, just to save a line of work in, so all of these terms with the i's have got just a single I in them. So basically I is a common factor. So I was going to put all the I terms and then pull out the common factor, but to save a line of work in, let's pull out the common factor on this line. So I'm just going to move this over. So it's going to be I times all the terms beside the I. So x for the first one, then negative x cubed over 3 factorial. Then the next one would be plus x to the 5 over 5 factorial, and then the next one would be negative x to the 7 over 7 factorial, and then that would continue. You can see the alternation here, and then plus blah blah blah. And if you're attentive here, you might be able to see what is going on in this derivation. So if you think back to the series that we saw earlier, the sine and the cosine, and well, we've already used the e, this should look very familiar. So this here is just the expansion, the Maclaurin series expansion for the function cos x. This here is a Maclaurin series expansion for the function sin x. So we're pulling together those Maclaurin results. Remember that what we've got here on the left-hand side, and this is still really important, is e to the ix. So what does that tell us? Well, that tells us then that e to the ix is just equal to this guy here, which would carry on forever, which is just the function cos x. Then we've got I times the function sin x. And in fact, at this point here, this gives us something called Euler's formula. And Euler's formula is basically what we derive on the way to Euler's identity. In fact, Euler's identity is really just a special case, I guess, of Euler's formula. So this guy here is Euler's formula, which is still a really important and useful result in its own right. How do we get from this to the result we're looking for? Well, we remember that this is an identity. Remember, identities are equations, but they're equations that are true when you sub in particular values in all positions for like the x. So sometimes they're written with 3 little lines like that. So we can choose, our variable here is x. We can choose any x value we want, and this should hold true. So we want to choose a convenient value for x, and the convenient value we're going to use for x is the value pi. So pi in the sense of pi radians. and well, in this case pi radians, but also just the, the number pi, and we're just going to basically sub that in. So what does that give us? Well, just to pull this over here, that would give us e to the I pi, so e to the I pi equals the cosine of pi plus I sine of pi. Thinking about these, so the cosine of pi, thinking maybe about the cosine graph, if you're familiar with trigonometry, which I'm sure you are, then this would be e to the I pi equals -1. The sine of pi, that's the sine of 180 degrees, remember, on a sine graph, so that's where the first sort of peak comes back down to the x-axis, so that's going to be 0. That's going to be I times 0, which is just 0. So you basically get a plus 0 on the end there, which we don't really need. And you can see we've almost arrived now at a result. So this would then imply, finally, let me put it over here, this would imply finally that e to the I pi, by taking the -1 to the other side of the equation, it becomes a +1, e to the I pi plus 1 equals 0, and that is our final result. That is Euler's identity. So it's a really cool proof. It basically pulls together these Maclaurin series that then allows you to make Euler's formula, and by subbing in this particular value for x, we're able to arrive at Euler's identity.